Good morning. Good morning. Good morning. Good morning. Yep. Okay. First of all, some housekeeping. So yesterday someone told me that he had a problem with one of the assignments, which is the assignment with the file int.c. And he tried to compile it under Sequin on Windows. So Sequin is something like a Linux environment for Windows, and it has been there like for ages now. So it's not the actual native Windows, well, Linux subsystem of Windows 10, but it's like a much older project. But in general, it works fine. So you can use that to run a lot of Linux commands on Windows, and also you can use it to well, compile a lot of stuff under Windows. It's quite popular, and for some reason the GCC compiler in Sequin doesn't like to compile int.c. So is there anyone else in the room who is using Sequin and you? Okay, so I had a look at it. Actually, I do not even understand the error message. I had a look again at the code, and the code seems to be correct. Okay, also I make mistakes when I write stuff, but I looked at it very carefully and I couldn't find any obvious problem. And also, in like every other environment, it doesn't even give me a compiler warning. So I have no idea what's going wrong there. Currently, I would assume it's a bug in the Sequin environment. So maybe updating helps, and I have no idea what's happening there. So for all of you who are using Sequin and you get the same error message, I would recommend maybe try the same thing in Linux VM, or maybe try, the standard, the Linux environment that comes with Windows 10. Actually, I never tried it, but might work. So I have no idea what's happening there, and so far I cannot help you with that, and I even don't understand the error message. Only thing what I can say at the moment is that the code itself, it seems to be correct. So I would rather assume it's a bug in the compiler, but on the other hand, Sequin is quite popular, so this code isn't using any weird features of C. So when there would be a bug in the compiler, I would expect it to appear at a lot of places, so it should be fixed rather quickly. So maybe even updating Sequin from time to time helps. Besides that, there are no expected problems with the current assignments. Are there any other questions about yesterday's lecture? Actually, the screen is supposed to be on. Oh, there was a mute button. Great. So let's continue with concurrent programming. So yesterday we had that example of count.c. It's basically the same thing what the Java version does, but here, it's written in C, and the mutex is used, which is the which is a semaphore. Well, the semaphore is used called mutex, which is the equivalent of the Java semaphore. And what we have here is roughly a critical section. So when those lines of code are executed, no other process is supposed to execute that in parallel. So it's locked with the semaphore here. Semaphore is initialized here. And then we create two threads, and one is supposed to create upwards, and one is supposed to create one is supposed to count upwards, the other one is supposed to count downwards. So we have our target parameters here, and this one is 1 and this one is -1. And as long as we run the code without an argument, then it sometimes works, sometimes it fails, because there is an assertion failure. So we have an assertion here in our code. So we check at the end whether a counter is 0, and when it's not 0, then it's obviously a mistake. And when we run the code with an argument like this, then we actually use the semaphore. Then we do not necessarily get always the same result, but at least we do not get the assertion error anymore. So are there any questions about this code so far? No. So let's have a look at what a semaphore actually is. Does someone still remember from the last lecture? What is a semaphore? Why not? Look it up in, well, your notes. Yeah.
It's a mechanism that enables you to specify a block through which only one thread, or as you specified, can execute.
Well, yes, that's what we use the mechanism for. So it's a mechanism that we can use to make sure that only one thread, or alternatively, just a specific number of threads may execute a certain section at the same time. But what are the properties of a semaphore, or how it's actually implemented? Yep.
It's a variable that changes on conditions.
It's a variable that
Changes on certain conditions.
on certain conditions, yes. And there is a certain invariant of this variable, which is, so we initialize our variable with a value. So here it's a natural number, 1, and always needs to be that natural number. And which condition is always true for a semaphore?
It's at least 0.
It's at least 0, that's right. That's one of the important things. And what's the other property? Let's go a bit back into the slide. So, B. So first of all, it's at least 0. And the value is always the initial value plus the number of signal calls minus the number of wait calls. Okay, and here in C, it's not a signal and a wait call. It's it's a wait and a post call. So with that, it's a variable, it's natural number. So why can't we use just an int? So we can use an int for counting, right? What prevents us from using just an int as a semaphore? Yeah. No, I assume, well, okay, let's say long int is 64-bit. That should be enough for pretty much every realistic scenario. And I also don't assume that you will have semaphores in any real code where you would love to have more than 2 to the power of 31 minus 1 threads at the same time, the same critical section. So assume that the maximum value is quite okay. Yep.
Semaphore also implements a wait function, so it can wait before it's 1 or higher again.
So we have those functions for the semaphore, which is wait and signal. And when we call wait, then it's effectively decremented. And well, when we cannot decrement it without it becoming negative, then we suspend the execution of the current process or thread. And for signal, we notify one of those suspended processes, and we increment it, or we increment it. And that cannot be implemented with an int easily. Okay, so at least we have a problem that we cannot implement something like increasing or decreasing a certain integer in atomic statements, because this might result in like 3 machine instructions, such as a load, an add, and a store. And, well, I'm not sure actually what the exact names for those instructions are on the ARM architecture, and also depends on what kind of data type you're processing. And also we cannot implement something like suspension of the execution of the current process in a very useful way, at least not without support from the operating system. So when you look at this code, you might come up with the idea that we need support from the operating system to implement a semaphore. At least that we can get the suspension of a specific thread. So, how in general does your program get something from the operating system it wants? What's the standard mechanism for that?
System call.
Yes, a system call. So, find out which system call is used to implement a semaphore. You know how to do that, right? Okay. Maybe one important hint for the count program, so you can just run trace, and when you cannot find the right system call, alternatively you can just comment out most of the count code and write a very small C program that basically just calls semaphore init, print something, and then wait and post. So you can, when you don't succeed with the count example, write a very minimalistic C program that just initializes a semaphore, calls wait once, and then calls post. And between that, you can add printf statements. So with the printf statements, it's maybe a bit easier to figure out which system call exactly it is. So any results? Yep. Vutex. This one here, right?
Yes.
Yep, that's right. Vutex was used. So every time when we, more or less, when we do a semaphore operation, we use the Vutex system call. And what might be required here is we use trace minus F when there are multiple threads. But yes, you can see there is a Vutex system call. And when you can also, when you like to, you can try the same for the Java virtual machine. So we also had the count example in Java. Takes a while to compile. We can also run trace on that. And we see that there are about 261 syscalls by the Java version, but we haven't used trace minus F, so actually needs trace minus F. Then we get 3,000 system calls by the Java version. And when we run trace on the C version, we just have 242 system calls. So the Java implementation seems to be, at least for this tiny example, a bit more inefficient. So the C version in total uses 242 system calls. The Java version uses over 3,000 system calls to achieve basically the same thing. So when you use trace on Java program, very often you get a lot of overhead, and it's a bit more difficult to figure out what it's actually doing. So yes, Vutex is used to implement the used to implement the mutex here, well, the semaphore here, and it has a certain overhead. So, well, the semaphore is just one thing that you can do to protect the critical section, but there could be even more. So let's have a look at another example. So this is a bit. So this is a bit more. Well, that's another way how you can actually achieve something like a protection of a critical block or an atomic update. So at least in the Linux environment in C, you have a command which is called sync, bool, compare, and swap. And you can try to figure out what it does, but I think I'll just tell you. It's basically an atomic operation. So when you call sync, bool, compare, and swap, then it will take the first argument here, log, which is an integer. It will compare the value that, which is actually a pointer towards an integer. It will dereference that pointer, look at the value here, which is currently 1, compare it with 0, and when it is equal to 0, which it is currently not, because currently it's 1, or it's initialized with 1 at least, then it will swap it with 2, and it will return true. And when it's not equal to 0, it will return false and not swap it. So what it does is effectively it dereferences the first argument, compares it with the second one. When both values are equal, this memory here is swapped with the third argument. And when not, then it's not swapped and it returns false. Otherwise, it returns true. So it's a way of doing atomic updates of your memory and also knowing whether the update was successful or not. So, and what's implemented here, it's basically what we would like to do is we would like to wait until this variable here becomes 0. And when it's 0, it's swapped with 2. And as long as it is not 0, we call scat.yield, scat underscore yield. So scat underscore yield tells the operating system that this might be now a good time to schedule another thread. The reason why we call it is pretty simple, because we are waiting for log to become 0. And the only way how log may become 0 is because another thread updates the memory to 0. So the best thing what we can do in this moment is just to wait for another thread to do that. So we could also just remove this get yield instruction here. Then it would more or less run in a loop and continuously burn CPU time. But it would very likely not, it will not be suspended. So the nice thing is when you have, do you still remember the example here, Concurrency? So we initialize our mutex with our semaphore with 1. What would happen when I replace that with a 0? Anyone still knows that from the last lecture?
It would never, or it would forever wait if it needs to wait.
Yes, it will wait forever, but, well, that's the bad news. But the good news is it will do that very efficiently. So, here we are, we defined the semaphore in a way that when the semaphore is not greater than 0, then we suspend the execution of the current process. Well, actually, I don't need it. So, we run count, and as long as I don't give an argument, it will just, run and fail from time to time. When I now use the semaphore, then it blocks forever, but that's the bad news, but the good news is, when I run top, then the system is pretty much idle. So the execution of the count program is suspended because everyone just waits for, we have 2 threads. Both threads wait for the semaphore, which will never become available because it's initialized with 0. And the main thread waits for the execution of the other 2 threads. So that's also implemented in a very efficient way. So when you just call thread.join, then you don't burn any CPU time. And the alternative solution to our problem is the atomic sync bool compare and swap instruction, which is also a way of waiting for, actually this time it's really an integer. It's waiting for an integer to have a certain value. But this is, at least when it comes to burning CPU time while waiting, it's not that efficient. So would all recommend compile that program, run it, and when you like to, you can replace the sleep 1 here with something like a sleep 10, and then you can look in top and see what happens to the process. So how much CPU time it's burning, and how much, well, what's the system load, how it changes. So now, try compiling that program, run it, and because here it will just, well, what will actually happen is it will create this thread here, which will wait for a second. Then it will update log to 0, so that this condition here becomes true. And the for loop is terminated. And because it's only a second, that can be a bit hard to observe on top. You can also change that to 10 seconds here. And then give it a try and see what happens to the CPU consumption on the Pi. So which result did you get from the program? What happens when you run it? So what is different here when you compare it to the previous example where you had the count program with the modified semaphore and it was stuck waiting for the semaphore?
CPU usage?
Yes, the CPU usage here is actually pretty high. So this is the unmodified version that I'm running here, which just runs for a second. And what is the last number that is being printed here? What does it represent?
How often it waited? How often it cycles through the scheduled use?
Yes, so it tells you how often this loop here has been executed. And the result is about 55 million times. So within a single second, apparently 55 million times, it has executed the loop here. And the reason for that is it hasn't been compiled with the yield flag. So the well, the execution of this get yield command here depends on compiler flag, which is called yield. So when you do that with -d yield, you will get a different version. And now get yield is actually called. So without get yield, you get 55 million executions. Now try with get yield enabled. How many executions do you get? Or, well, first of all, let's think, what would you expect? We have a for loop here. And the first thing that we did was basically just execute that sync bool compare and swap instruction. In a loop for 1 second. So that means we get about 55 millionth execution of the sync bool compare and swap instruction. And of course, there are like conditional branches, increasing I, and other stuff. So what would you expect when you also call get yield in the loop? Will it get faster or slower? Who's for faster? Raise your hands. Who assumes it's slower? Okay, why should it be faster? Or why do you think it would be slower?
It would not be slower, I think, but it would enter the for loop not as many times as before.
Yes, okay, sorry, I was a bit unprecise about that. So it didn't ask about slower or faster, but would you rather expect that the loop is executed more often or less often? So you think it wouldn't be executed?
I think it would be executed less often, because with get yields, the thread or the process gives up the current CPU time, and then other processes can use it, and then somehow later, at the end of the queue of processes, the thread is being executed again, and then it enters the for loop again.
Yes, so first of all, it might be more likely that other threads running on the system will get some CPU time. Well, by default, that's not a lot. So effectively, there are some background processes running on your Pi, and well, there is stop running and the SSH daemon. So they don't consume a lot of CPU time by default. So, but in general, yes, it will be. You could expect it to be slower. So you could at least there should be some overhead by using get yield. So what you do now is first of all change the parameter for sleep back to 1, as it has been previously, and then run it. Well, compile it with -d yield. Then run it and then figure out which numbers you get. Well, and after that we should take a break. So see you again at 9:50. And then we will compare the numbers. So, break is over. Let's look at the numbers. So, first of all, I had those were executed on a Raspberry Pi 3. So when you have a Raspberry Pi 2, is there anyone here with a Raspberry Pi 2? Or 1? Raise your hands, please. Yep. Did you try without the D yield? Okay, you can try, and would be interested in what kind of number you get. So the Raspberry Pi 3 gives you 55 million roughly, And I wonder how much slower or maybe even faster the Pi 2 is. Okay, you have a question? Yes. Yes, so what does the yield do? What the yield does isn't actually that hard to explain. So we have our code here, which is more or less C code as you know it, except for those 3 lines here. And what I've written here is if-def. And if-def is basically almost the same as an if. Of course, you all know what an if statement is. So who of you has ever seen if-def? Raise your hands. Okay, not that many. So basically, if-def is something like an if statement, which is not executed while the program is running, but instead it's evaluated at compile time. So what you're saying here, if the variable yield has been defined, and there it's a variable of the C preprocessor. So you're saying basically if the statement here is true, then add this line to the source code of the program. And why not, don't do it. So what I'm basically saying here, I'm effectively have 2 programs here. And one program contains this yield instruction and the other one does not. So with -d, I can define certain variables at compile time. And effectively what happens here is so I'm just copying that to 2 functions. Spinlog1 is effectively an empty for loop, and spinlog2 is the for loop with the yield instruction. So effectively this command line flag for the compiler here lets me switch between spinlog1.c and spinlog2.c. So with when I specify d yield when I'm compiling the program, then I'm effectively compiling the version in spinlog2, which contains the yield instruction. And when I'm not compiling it with -d yield, like this one, that's effectively the same as this one. So not specifying d yield gives me the code in spinlog1.c, which doesn't have any yield statement here. And specifying -d yield gives me the code in spinlog2.c. So spinlog1 doesn't have the yield instruction, and it behaves more or less exactly as the one that we have seen previously. Okay, now it's 56 million, but 57. So this one here is effectively the version without the yield. And when I specify -d yield, I get the version from spinlog2.c, which contains the yield instruction. That is something that is not supported by Java. So by Java, you cannot really enable or disable specific parts of the program at compile time. But there, the most interesting stuff happens at runtime. And in C, you can say, okay, I have certain statements in my program that I only want to be part of my program under specific conditions. And probably the most common use case for that is by having a variable here that is called debug and having some additional printf statements in your program. So when you have problems with your code, you can write something like if def debug. Then you add some printf statements that prints the current state of your program. And when you compile your program -d debug, then it will contain those printf statements. And when you don't compile it with -d yield, then it will not contain those statements. And the advantage of that is that you can have a rather small binary without all the debug statements, which is more efficient than having a big binary with a lot of if we are in debugging state things. And it gives you other advantages. So when you can say, okay, I would like to compile a version of my code with, for example, debugging instructions. When I would do that in Java, I would say something like if the variable, like if debug, like I would have a variable like a Boolean debug. And when my program is running under debugger, in debugging environment, then I would set the debug variable to true. And then I would always say in my code, if debug, then system out print line, the current state of my variables is, and something like that. And the problem with that is that the code gets slow, because during the normal execution, when debug is false, there are a lot of conditional branches in your code, and that might be a bit slower. And in C, you can actually remove all the debug statements at compile time, which is sometimes an advantage for speed, which is sometimes a disadvantage for debugging, because when you would like to debug your program, you have to compile a specific debug binary. And as you know, depending on how the bug looks like, it might not appear in the debug binary because it may depend on a certain memory layout or things like that. Any more questions about the yield or the if-def statement? No. Okay, so we are now trying to collect numbers. I've now compiled the program with yield. And which numbers did you get with the yield enabled?
About 1 million.
1 million. Pi 3? A Pi 3?
Yeah.
1 million. Other numbers? Half a million. Did you use a Pi 2 or 3? 3, okay. Any more numbers? So what does it tell you?
Without the yield, you get more steady results?
To some extent, yes. So with the yield, when you play around with it, very likely with the yield instruction enabled, it will vary much more depending what else happens on your Pi. But also, apparently, the yield instruction is 50 to 100 times slower than this instruction here, sync, bool, compare, and swap. So what we have here, it's apparently something very efficient. You can do that 55 million times in a second on the Raspberry Pi. And the Raspberry Pi isn't a particular fast computer, it's rather a slow one. So now comes the interesting part. try to figure out how sync bool compare and swap is implemented. How would you do that usually? And when you do that, make sure that you compile it without, well, you can try to compile it with or without the yield. So what does trace tell you? What do you think what the sync bool compare and swap actually is? So what do you see in this trace output? No, because actually when it would be a few ticks weight, you would see that a lot of times in the output. Apparently it's used 55 million times, but we do not see a 55 million syscalls here in this trace output. So when we run the code, and we can also run it with, instead of sleep 1, we can change that to sleep 10. When we run it, we see nothing. So whatever it is not a syscall, because when it would be a syscall, then it would appear here in this trace output. So it's something else. And what it actually is, it is a hardware instruction. So you can do those things without support from the operating system. And it's a single machine instruction. So it's compared to a syscall, which has some overhead. It is much faster. So we just had this get yield syscall, which at least most of the time does nothing, because there is nothing else to schedule. So when you compare the sync bool compare and swap instruction with the get yield, apparently that thing is about 100 times faster than a syscall. So when you need to update the memory in an atomic way, and you would like to do it without a semaphore, you can actually use those instructions. And the good thing about them is, as long as, well, there is no one else holding the logs, so the memory is in the state that you expect it to be in, then this thing is much faster than any kind of semaphore, syscall, whatever. It's a single machine instruction. And when you would actually like to see what it does, there is a command called object dump, which is effectively a decompiler. So when you run object dump -d spinlog, you see all the machine instructions in the code. So who of you learned ARM assembly in the first part of the module? Raise your hands. Okay. Then you can actually look into this and try to understand what is happening here. I can tell you it's effectively a simple machine instruction. So this is in general often called a spin log, because effectively you're spinning around in a loop until you have acquired a log, so until you have managed to update the memory to a specific value. And this can be a very efficient way of handling logs, because what you have seen is we had those example in the beginning of the lecture, like the count example, and sometimes count was successful. Or also the Java version, sometimes when we executed it without a semaphore, it completed successfully, so it didn't corrupt the memory, it counted correctly. Sometimes it did not. It just means that apparently there is quite a good chance that, both threads never enter the critical section at the same time. So there is a good chance that it doesn't corrupt your memory. But usually you don't want to bet on that. It just tells you whenever you have a program where it's very unlikely that another thread at the same time might hold a specific lock. You may want to consider using spin locks instead of mutex, because then this will be much faster. So when the likelihood of another thread occupying the lock is very low, maybe have a look at spin locks. Very likely this could be a much faster thing than using a semaphore. On the other hand, when it's very likely that another thread will occupy the lock, then a spin lock can be very inefficient because your program will continuously burn CPU time while waiting for a lock. So in general, you don't want that. So it's a bit hard to make a decision about which mechanisms you use. You could either use the spin lock, you can use the semaphore. Semaphore by default has a bit more overhead. On the other hand, the overhead is rather constant when the lock is occupied. When you use a spin lock, then, actually acquiring the lock when it's not occupied is like instant. It's basically just a single CPU instruction. On the other hand, when the lock is currently occupied by another process, then you're in a problem. Okay, any more questions about spin locks? No? Then, look at the advantages, disadvantages. So one of the advantages, it's rather simple. So you just need that atomic instructions there. You can use it whenever you have shared memory. You do not need support from the operating system. So you are more or less independent of the operating system. On the other hand, you need support from the hardware. So there might be some architectures where there is no suitable hardware instructions. And when you are on such an architecture, then compiling this code will simply fail. So it will tell you that it cannot generate program because there is no simple compare and swap instruction. So on some architectures there is such an instruction. Luckily with the Pi you are on such an architecture. Luckily your computer will also have one, but it's possible that you're compiling code for an architecture where there is no such instruction. And the disadvantages is when you have to wait for a lock, it will cost a lot of CPU time, and there is actually starvation possible, which means that you have effectively two threads. So when you look at those things here, you have two threads. Both are waiting to get a lock for a critical section. And when you use spin locks, it's actually possible that after that here, the thread more or less loses the lock, so that's the memory back to 0. And then right after that, it acquires the lock again. And thread 1 is always unsuccessful because whenever thread 1 is scheduled, the lock is occupied by thread 2. It's possible, and it maybe also happens in practice. So when you have a lock that is busy like almost all of the time, then it's possible that one thread will never get the lock. Which also means that it's possible that you write code that will simply not terminate. Okay, so far we only had semaphores, and we initialized them in a way that we had only one process at a time in a specific critical section. But that's not the only way how we can use semaphores. So of course you can use semaphores as we used them in the previous examples, which just was initialized to the value 1, so it will have only the value 0 when it's basically blocked, and it will have the value 1 when it's available. But we can also initialize semaphores with another value. So for example, what we could do is, and what is very common is, that you have a cyclic buffer, or also called a ring buffer, as a kind of communication channel between two threads. And a cyclic buffer is effectively an array in the memory, which has two pointers. One is the in pointer, so that points towards the first free address in the ring buffer, where you can write data. And the other one is called out, which is the location where data can be read from. So the occupied sections of the buffer here are marked in red. So that means that currently B4 is occupied. So when there is one process that would like to take something from the buffer, it can take it from B4 here. And when a process would like, or a thread would like to write something to the buffer, it can write it to B1. That's a very common scenario. And what you get very often is a producer and a consumer. So for example, when you go back to the first slides that you have seen, where we had built those pipeline with the sort command and the PR command and the get command and the unique command and so on, effectively it's the same scenario. So we have a process that produces something. At the beginning it's cat that produces something. And then we had a process that consumes it, which was the sort process. And we just used the pipe in Linux to establish a link between those processes. And what probably happened in the background is that there is some kind of cyclic buffer, and everything that the cat process writes goes into that buffer. And everything, whenever sort tries to read something from the standard input, then sort takes it from the buffer. In general, we call those processes consumer or producer. And I have an example here of a consumer and a producer. So when we look at the code, we have two threads. So we have one that's a producer, which puts stuff into the buffer, which waits for a semaphore, and then it puts something into the buffer, which is I, and then it increments the kind of index by 1, modulo n, which is the size of the buffer, and then it releases the semaphore. Then we have our consumer, which tries to take something from the buffer, which uses another semaphore called elements. And then it takes something from the buffer, prints it, and then increments the out pointer. So that corresponds to the scenario here. So we have an out pointer, we have an in pointer. B is our buffer. And we do have two semaphores here. So we have spaces and elements. And those semaphores are initialized with a different value here. So by default, elements is effectively the number of elements that are currently in the buffer that can be read. And spaces is the number of available space in the buffer, which is initialized with n, which is the kind of the size of the buffer. And here on the slide, only the consumer part is shown. So the producer part is not part. Oh, well, it's actually also part of the code. Great. So we have the main method just missing. So effectively what the main method just does, it creates the semaphores. It creates both threads. And then it lets the producer produce stuff and put it into the buffer, and then it lets the consumer consume stuff from the buffer. So every time when one element is produced by the producer, elements is effectively increased, and every time an element is consumed by the consumer, element is effectively decreased. We can also try to run that. Oh, I cannot compile it to broadcons because it's a directory. And this is the output that we get. So what happens here? The producer fills our buffer with 1, 2, 3, and then the consumer starts consuming stuff. So every time when you see this I equals 0, it's part of the consumer. So the consumer prints this value here, I equals the stuff here, and it shows you what's in the buffer. Every time something is added to the buffer, we get B is assigned to a certain value. We can, of course, alter the behavior of the program. For example, we can let it run a bit longer. Then we get more output. And of course, the output here isn't deterministic. So, to some extent, it could happen that, like, this consumer is lucky to get a lot of CPU time, and then the consumer will be able to read a lot of things from the buffer, or the producer is lucky and it gets a lot of CPU time, so it will be able to write a lot of elements to the buffer. But once the buffer is full, then the producer cannot write anything to the buffer anymore. So for you, look at the code and try to figure out under which condition the producer is blocked. So what are the state of the semaphores so that the producer cannot write anything to the buffer anymore? So what blocks the producer? What prevents it from writing more stuff to the buffer? Yeah.
The spaces semaphore is 0.
Yeah. So how is spaces initialized?
That's the full range of the buffer.
Yes. Yes, so we have the buffer B here of size n, and the semaphore spaces is initialized with n. So we have, well, n elements that we have space for n elements in the buffer, and initially we have 0 elements in that could currently be read in the buffer. So what we see at the beginning is, should better change that back to 10. So in the beginning, apparently here, the producer is lucky. It can write up to 4 elements to the buffer. Then it's blocked by the semaphore. And then the consumer starts consuming stuff from the buffer. And apparently the producer is also quite lucky. So as soon as there's space available in the buffer again, it can start putting new elements into the buffer. At the end, there are no more elements. Well, the producer more or less terminates. And then the consumer can read all the remaining elements from the buffer. And, okay, now something has changed. So apparently here, the producer was a little bit less lucky. So the consumer had enough CPU time to consume 3 elements from the buffer. And even while there was still space in the buffer, only after this line, the producer was again able to write something to the buffer. So kind of the output of that program is also kind of undefined, but it's guaranteed that you will never see more than 4 elements in the buffer, and it's also guaranteed that everything will be produced and consumed in order. And having such a kind of ring buffer in memory is a very common way how you can interact between 2 processes, and also it's a very useful way of using semaphores with another value than 0 for the initialization. And so far we only had 1 producer and 1 consumer here, but that's not the only scenario. So it's also likely that you have more than 1 program that generates stuff, or more than 1 thread that generates stuff and that puts things into the buffer. You could also have more than 1 program that takes stuff from the buffer and consumes it. And we only needed 2 semaphores here, the spaces and the element semaphore. And I think in one of the assignments you will look into this and you will figure out what you can do when you have more than 1 producer or more than 1 consumer. And then this will not work as it is done here, because you have a critical section and you need to update those variables in a like atomic way, and you need to read them in a kind of atomic way. So you need some more locking here. Okay, I think we don't have time to go into detail for the next things. So see you again tomorrow, and tomorrow we will continue with many producers and 1 consumer. And in the assignment you will investigate those things a bit further. So see you again tomorrow morning. Then we will look into producers and consumers when you have more than 1. And we will also look into another way how you can exchange data between 2 processes or threads.